Welcome to this explainer. Today, we're taking a really fascinating visual journey straight into the physical mechanisms of the ADHD brain. For decades, attention deficit hyperactivity disorder was mostly defined and understood from the outside, right? Just by observing behavioral symptoms, things like fidgeting, distractibility, or impulsivity. But what if we could look past all that behavior and actually see the unique wiring and the chemical landscapes that drive it? Well, thanks to advanced neuroimaging, we don't have to guess anymore. We are going to explore some absolutely groundbreaking studies that completely shift how we understand this condition, from chemical deficits to structural wiring, and even how the brain dynamically adapts to the very medications used to treat it. So, what does ADHD actually look like in the brain? Okay, let's dive into this. It's one thing to say someone has a short attention span, but what does that actually look like on a biological level? To answer this, we kind of have to transition away from behavioral checklists and look directly at the neurobiology. For a really long time, the exact physical signature of ADHD was totally elusive. But as brain imaging technology evolved, scientists began to pinpoint specific structural and chemical differences. And our journey begins deep inside the brain's motivation center. Section 1. The dopamine reward deficit. Back in a landmark 2009 PET scan study, researchers at the U.S. Department of Energy's Brookhaven National Laboratory looked at 53 unmedicated ADHD patients to measure the physical abnormalities in their dopamine reward system. Now, to understand what they found, we need to define a crucial player in the brain: dopamine transporters. Imagine dopamine as a chemical messenger, right? One that delivers a reward or motivation signal between your neurons. Well, dopamine transporters act like the brain's cleanup crew. Their whole job is to take up and recycle the excess dopamine from the synapse after that reward signal has been successfully sent. By injecting a safe, tiny amount of a radioactive tracer that binds specifically to these transporters, the PET scanner could measure their exact concentration. And what the researchers found was that, compared to healthy controls, the unmedicated ADHD patients had significantly lower levels of these dopamine transporters, as well as dopamine receptors, in two key regions, the accumbens and the midbrain. And these are the exact areas directly responsible for processing motivation and reward. And this brings us to a really profound insight from the lead author of that study, Dr. Nora Volkow. She noted, these deficits in the brain's reward system may help explain clinical symptoms of ADHD, as well as the propensity for complications such as drug abuse and obesity. So the crucial point here is that conditions like severe inattention or a lack of motivation aren't just personality quirks. They aren't a lack of willpower. They are directly correlated to a literal physical lack of dopamine markers in the reward pathway. Furthermore, it completely explains why some individuals with ADHD might unconsciously turn to overeating or substance abuse. They are intuitively trying to boost a chronically deficient reward system. Section 2. Two types, two networks. So we know ADHD isn't a monolith, right? Behaviorally, we typically see the predominantly inattentive type and the combined type. In a 2022 study by Saad and colleagues, researchers asked a brilliant question. Do the brains of people with the combined type literally connect and communicate differently than the inattentive type? Like, do these different clinical presentations actually have totally different neural signatures? To answer that, they looked at the default mode network, or the DMN. Think of the default mode network as the brain's idle or screensaver mode. It's this network of brain regions that becomes highly active when you aren't focused on the outside world, when you're just daydreaming, recalling memories, or engaging in internal thought. Now, for optimal cognitive performance, your brain needs to effectively suppress or turn off this screensaver mode when it's time to focus on a demanding external task. But in ADHD, this suppression is often highly inefficient. Now, what's really interesting about this mapping of functional connectivity is how it uniquely differentiates the combined type of ADHD from control groups. The 2022 study utilized functional MRI scans on children and adolescents and applied graph theoretical analysis. And they discovered that individuals with the combined type are uniquely characterized by reduced network connectivity within the DMN network itself. But it doesn't even stop there. The combined type also showed reduced connectivity between the DMN and other crucial networks, like the somatomotor and limbic networks. So it turns out that ADHD combined and ADHD inattentive don't just act differently on the outside, they literally feature fundamentally different large-scale intrinsic network wiring on the inside. Section 3. The medication plot twist. Okay, so we've seen that ADHD involves clear deficits in the dopamine reward system and distinct wiring issues in brain networks. You'd think the story of the dopamine transporter would be pretty much settled, right? Less transporters equals ADHD. But a massive 2012 meta-analysis by Fissar-Pauly introduced a huge plot twist. When they combined data from 9 different PET and SPECT imaging studies, encompassing almost 350 individuals, they found something completely startling. On average, the ADHD patients actually had a 14% higher striatal dopamine transporter density than the healthy controls. Wait a minute, didn't we literally just look at the 2009 study showing a deficit of these exact transporters? How on earth could a meta-analysis show they are actually 14% higher? This glaring contradiction built immense narrative tension in the scientific community. I mean, it forced researchers to ask a real chicken and egg question. Is this abnormally high density of dopamine transporters the root biological cause of ADHD, or is it a secondary effect? To solve the mystery, the researchers had to look closely at the clinical histories of the specific patients in the studies they were analyzing. And this brilliantly illustrates what they found. Notice the downward sloping line in the data. The researchers discovered a massive correlation. The lower transporter levels were consistently found in studies where the ADHD patients were drug naive, meaning they had never been treated with medication. This perfectly matches our 2009 Burkenund study. But the higher transporter levels correlated incredibly strongly with patients who had a history of taking psychostimulant medication. The medication history alone accounted for nearly half of the overall variance across all these studies. Let's move on and see how this builds a completely new understanding of the treated ADHD brain. The high density of dopamine transporters isn't the key pathophysiology of ADHD at all. Instead, it's the brain's adaptive response to the medication. Psychostimulants like methylphenidate work by aggressively blocking dopamine transporters, leaving more dopamine in the synapse to improve your focus. But the brain is highly plastic. Sensing that its transporters are constantly being blocked, the brain responds by physically creating more of them to compensate. And this creates a fascinating objective cycle of adaptation. Step 1. Medication blocks the existing dopamine transporters, which provides that immediate clinical relief and focus. Step 2. Over months and years of chronic treatment, the brain adapts to this blockade by upregulating, meaning it manufactures a higher density of these exact transporters. Step 3. Because there are now physically more transporters clearing out dopamine, the original dose of the medication might not block enough of them anymore. This beautifully and completely neutrally explains a very common clinical phenomenon, why the clinical effectiveness of ADHD medication can sometimes wane over the years, often requiring higher doses to achieve that exact same therapeutic effect. From a definitive lack of dopamine markers in the reward pathway to uniquely wired networks in different clinical subtypes, all the way to the brain actively rewiring its own transporter density in response to medication, the physical reality of the ADHD brain is just wonderfully complex. But it leaves us with a pretty provocative final thought. If our neuroplastic brains are capable of physically adapting so heavily to the treatments we provide them, literally altering their very structure over time, what does the future of ADHD therapy actually look like? As we map these networks and adaptive responses with greater precision, we're edging closer to an era where we don't just treat the symptoms, but we work in harmony with the brain's incredible capacity for change. Thank you so much for joining me on this explainer, and keep questioning what you think you know.